chapter 4 tomorrow. All right, sorry, I'm recording now. Last week, it's been a while since I've seen you because you guys know that we had no school on Thursday, no classes on Thursday. But last Wednesday, if you can remember, we looked at some of the reactions of alkenes. We looked at basically adding hydrogen halides to alkenes, and we did this practice problem. Well, today I'm going to do a couple more reactions, and then, like I said, that's it. I just want to finish chapter 3 today, and I will be a happy person. So, this type of reaction is very similar to adding a hydrogen halide, or HCl, HBr, except in this reaction, we're adding a straight up halogen like X2, or sorry, not X2, a Cl2, Br2, something like that. So kind of a pretty simple reaction here. Unlike adding something like, say, HCl, where the hydrogen goes on one and the chlorine goes on the other, if you add something like Cl2, Br2, each element, or atom or element in this compound goes on each carbon across the double bond. They kind of split themselves equally. So it doesn't matter if you go up or down. I don't really care. Typically, they would be opposite each other because of the space. Remember, chemistry 1120, valence shell electron pair repulsion. The idea, and you don't need to know that for this course, but typically one would go on the top and one would go on the bottom to kind of spread themselves apart, so they're not kind of crowded. So let's look at okay, we'll look at an example in a minute. I have another example here. This is something we used to do. So again, I'll come back to this. I'll show you an example in a minute, but this is another example. This is a reaction that we used to do in the lab. Well, I shouldn't say we used to do it. We tried to do it in the lab, and we had so many problems trying to get this to actually work with the chemicals we had available. And I think a big problem was our distillation wasn't really cold enough to make this, to get a good product. So this used to be, I think, lab 4 or 5, but now we had to kind of cancel that lab. An alkene can also react with water. However, now remember, hydrocarbons and water typically do not mix. You can get this reaction to happen with some help. You typically need a strongly acidic catalyst to get this reaction to help, or to get this reaction to happen. So, if you just mix water with an alkene, typically nothing will happen. You need some help with this, and the help is usually a very strong acid. So this H plus, this H plus represents my acid. Now, one thing I want to mention to you, well, two things, is one, you already know how to do this because we did it when we added the hydrogen halides like HBr, HCl. We've already actually practiced this. The second thing I'll mention is it's really useful to think of water not as H2O, but as HOH, a hydrogen bonded to an OH. And this that is, again, review from chemistry 1121. When you talked about acids and bases, you might have learned that water itself is can self-ionize into an acid and a base. So when we did that in chemistry 1121, you guys probably had Miss Gabby or Mr. John or somebody, Miss Michelle, I don't know, but it helps to write H2O like this, a hydrogen bonded to an OH. Then what you do is you do exactly what we did last class on Wednesday. You follow the Markovnikov rule. I love that. I love saying that word, where the hydrogen in the water goes on the compound that has the most hydrogens, and the OH in the molecule goes on the carbon that has the least hydrogens. And I'm going to show you this now if you can't remember. So it follows Markovnikov's rule. If I look at this carbon on, so I'm going to look at two different carbons. I'm going to look at this guy. I've highlighted as yellow. I'm down in this molecule on the bottom, guys. So I'm here. And I'm going to highlight the other one as orange. And you really need to look at the carbons to follow this Markovnikov's rule. Now, again, if you weren't here on Wednesday, you probably haven't seen this before. Markovnikov's rule states that hydrogen goes on the carbon with the most hydrogens. The other compound will go on the carbon with the least amount of hydrogens. So if I look at this compound, this carbon has 0 hydrogens. This carbon has 1 hydrogen. So my hydrogen would join the carbon that has the most other hydrogens. It makes a more stable intermediate. This one down here is much less stable. And I think, again, this was a big problem we had in the lab trying to stabilize our product. We had some issues there. So this is basically the answer to the problem. This is, again, called a mechanism, which you guys do not need to memorize, but you do need to memorize, or sorry, I shouldn't say memorize, but understand the final product. The final product here, the hydrogen goes on the carbon with the most hydrogens, and the OH of the water goes on the other carbon from the double bond. I'm going to show you an example of this in a minute. One thing I'll mention, if you hydrate an alkene, the product you get is called an alcohol. It has the alcohol functional group right here. So yes, yeah.
Sorry, but you said it will go for the carbon that have more hydrogen.
Yes.
What's this mean? Because this is the CH3, it have also more hydrogen. Why it not go to the CH3?
Because the double bond wasn't there, right? Remember that the molecule we're working with is this molecule, and it can only add to the double bond. So I have two options. It can add to the carbon that has no hydrogen or the carbon that has 1 hydrogen. All of these reactions happen with the double bond. Does that make sense?
Yes, thank you.
No problem. Good question, really. Okay, let's just practice this. I think it's a lot easier for me to practice these. And then we're almost done. I only have a couple. Yeah, oh yeah, we're very close to the end here. Okay, so let's look at these practice problems. By the way, guys, there is a worksheet online for this. So if you want to practice these questions, there's a worksheet with answers online. I think the key for this type of problem is to practice. So let's look at these questions. I like these questions because, first of all, we need to sketch the chemical, and then we need to actually answer the question. So the first one, easy. 3-methyl cyclohexene. So let's draw this. Cyclohexene has 6 carbons. Okay, and on the third, so okay, cyclohexene would look like this. We have a double bond here. And on the third carbon, we have a methyl group. Sorry, just kind of clean up my drawing there. So this would be 3-methyl cyclohexene, and we're adding to that chlorine gas, Cl2. Now, there's no hydrogens here to worry about. We don't follow Markovnikov's rule, which I'm going to show you in the next 2 examples. All we do is add a chlorine to each carbon on that compound across the double bond. Across the double bond. Let's see if I can erase that without erasing my molecule. There we go. So we're going to add a chlorine to each carbon across the double bond. So when I get my product, it will look like this. The alkene is gone. Now it's an alkane. Okay, and on this carbon, we have a Cl, and on this carbon, we have a Cl. Now, typically, this would be trans, meaning one chlorine would be up and one chlorine would be down, but we're not going to worry about that for this section. Remember, the only thing you need to know about cis and trans is the naming, like not naming, but how to identify it. We're not going to worry about it for this example, but again, typically, one of these chlorines would be up and one of these chlorines would be down. All right, B, I got some questions about the lab. I'll get to that after I'm done teaching. So we'll talk about your labs after this, after I'm done the class. Okay, what about B and C? Maybe I'll do B and then maybe you guys can try C. So for B, I'll pick another color. Let's go with purple. I need to draw 3 heptene. So 1, 2, so heptene is 7. 1, 2, 3, 4, 5, 6, 7. And on the third carbon, I like to go from the left, 1, 2, 3. I have a double bond. Okay, so there's 3 heptene. And I'm adding H2O to this. Some of you guys might wonder on the left there, what's the point of the H plus? The H plus is just a catalyst. We put that over the arrow. The catalyst means it's not being used up in the chemical reaction. It's just helping it. Now I'm going to run out of room here. Well, I'll have to erase my answer in a second, but I'll do my answer below because I don't have much room. So my answer will be just below down here. Okay, the double bond disappears. Now, here's the interesting thing about this compound. Using Markovnikov's rule, it actually doesn't matter where I put the H or where I put the OH, because if you look at my carbons, so this carbon and this carbon, they both have the same number of hydrogens on them. This guy has 1 hydrogen. Sorry, let me write that again. And this guy has 1 hydrogen. Now, how do I know that? Well, remember, guys, every carbon must have 3, sorry, bad thing to say there. Every carbon must have 4 bonds. Every carbon has 4 bonds. So if you look at each carbon, they have 3 lines coming from it. 3 lines. We have the double bond and a single bond from each carbon. That means if they only have 3 lines, there must be 1 hydrogen as well. And as Naim said in the chat there, yeah, 4 is our magic number. So again, I know that there's 1 hydrogen because every carbon must have 4 things coming from it, and each of these only have 3. Sorry. Okay, so the 3 lines coming from it there. What that means is, for my Markovnikov's rule, or for my addition, it actually doesn't matter where I put my chemicals. I can have this, or, sorry, I had to kind of cram it in there. I can have this. And if you had this question on a test, I would accept both. I would accept just one or the other. I'm only asking you to write the major product. And in this case, it's basically 50-50 because Markovnikov's rule doesn't work here. The hydrogen goes on the carbon with the most hydrogens, but they both have 1. So it kind of doesn't matter, right? I mean, if you were in an organic chemistry university course and you were taking this a little more seriously, well, not that we're not taking it seriously, but if you were looking at it in greater detail, it would be about 50-50 in the real sample. Notice that these are not the same chemicals. We have 3 heptanol, an alcohol, and we have 4 heptanol. So you would see both of these products. Pretty interesting. C, wink, 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 wink. C is more like something you would see on a final exam or an assignment or something. C is an example that will follow Markovnikov's rule. Now, I have to, well, maybe I don't have to erase my notes, but just kind of take a mental note of what I have written there. Take a picture, and this will be up on YouTube. I'm a little bit behind on my YouTube, but I will have the videos uploaded this week. So take a little mental note of that, and let's look at the second one. I'm going to draw the second one, and then we're going to do the answer together. Oops, sorry. So let's get some more room here. The reaction is 2, sorry. So this is C, 2-methyl, man, this pen, 2-pentene. Sorry about that. And we're adding to that water and our catalyst. Okay, so step number 1, you have to draw the molecule, or you should draw the molecule. So I'm going to start with pentene. So 1, 2, 3, 4, 5. On the second carbon, I start my double bond, and I also have a methyl group, and I'm adding to that water with an acid catalyst. Now, this is what you would see, this type of question, wink, 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 wink. You would see this type of question on your test, and it's probably a good idea on your final. And it's really important that you practice this. You can use some of the worksheets I have online. All right, so what I want you guys to do, I'll give you a minute to try this. Oops, oh no. Sorry guys, my screen erased itself. Sorry, I want you guys to take a minute and try this. Naim just said my writing doesn't need to be perfect. I agree, but I want to make sure my molecule at least looks perfect. Okay, wow. It's like it's getting worse. Okay, so I'm going to stop talking. I'll give you guys a minute to try this. Now, you can just write it on a piece of paper. You can do whatever you want, but just try this. Definitely a question that you need to know, and I'll be back in 1 minute, so 60 seconds. I'll be right back. I forgot to hit resume record, so for the people watching this on YouTube who aren't or not here right now, this is the answer. The top is the answer. I forgot to hit record there. But yeah, so for the YouTube people, the hydrogen goes on the carbon with only 1 hydrogen, and the OH goes on the carbon with no hydrogens. It's Markovnikov's rule. Oops, not Markovnikov, Markovnikov. Pretty sure that's a Russian. That name sounds pretty Russian, doesn't it? Or Ukrainian or something. Okay, if there's no questions, just give me a couple more minutes. I just want to show you maybe one more reaction, and then we're done for today. All right, I'm going to get off this slide. So when I get off this slide, the slide will disappear. So make sure you kind of have a mental note of this. Again, this will be on YouTube, so you can check this out. Okay, so now I want to show you one more reaction, basically to kind of finish off this unit. There's a lot more slides here. We'll kind of talk about the last 3 slides tomorrow, and we'll also start unit 4 tomorrow. But I want to show you one more reaction. Now, good news is you do not need to memorize this slide. So this is slide 62, or I'm sorry, when I say memorize, you do not need to study this slide. I do want to show you though, or I did want to mention on this slide, that there is a way to actually break Markovnikov's rule, to kind of do the opposite of Markovnikov's rule. And what you would do is you would first react that compound with B2H6. It's called hydroboration. Basically, what you're doing is you're using this compound, B2H6, to force the opposite of Markovnikov's rule. And you get a really good product. You'll get about 90% of this product. This will not be on any, it's not in your labs, it's not on your final exam, don't worry. But I did want to show you that you are not forced to follow Markovnikov's rule. There are chemical ways around it. There's chemical ways around most things, to be honest. Okay, I want to show you one more reaction for today. And the reason I'm only doing one more is this one can be very confusing to students. So I'll show you one more and then we'll take a break for today and we'll kind of finish this off and get into chapter 4 tomorrow. This is a reaction you guys actually did in your lab. I think you guys did this in lab, I'm going to say 4. Definitely lab 4. So you did this a few weeks ago. You didn't need to know this to do the lab, so that's kind of why we're only doing it now. You can convert alkenes to alcohols or ketones by using permanganate. Okay, now you don't need to know the name, but the idea is adding permanganate, and in the lab we added potassium permanganate. You can actually break a double bond and turn it into alcohols, call this oxidation, and then go even further and turn it into ketones. Okay, so the big one I want you guys to know, and this is again what we did in the lab, is the oxidative cleavage of alkenes using permanganate. This is kind of the last reaction of today. Let's kind of break this down. Oxidative cleavage, what do those words mean? Oxidative means we're kind of adding oxygen, we're oxidizing a double bond into an alcohol, an aldehyde, or a ketone. We're adding oxygen across the double bond. So oxidative means adding oxygen. Cleavage means to cut something. It's like a geological term. The cleavage of a rock would be like the cutting of a rock structure, usually happens in nature. So cleavage means like a cleaver in a kitchen to cut something. So what we're doing here is we're cutting the double bond and adding oxygen across it. This is the most challenging of all of the reactions. And this is basically the last reaction you guys will need to know in chapter 3. And every semester I get a million questions about this. So this is something we'll look at right now. And I'll do a little review of tomorrow as well. It can seem quite complicated. So in a potassium, this is permanganate, MnO4 minus is permanganate. If you can't remember that, it's in your data booklet, not that you'll need it. And if you take potassium permanganate and mix it with an alkene, and it's a little bit warm, it's acidic, and the acid is concentrated, you will actually split the double bond. And I'm going to show you how this works. Initially, when the double bond splits, the double bond literally, you kind of like I'm not even joking, just cut it in half, and you get alcohols, but as you keep the reaction going, it will turn into aldehydes or ketones, like you can see here. And again, if you keep the reaction going, it completely oxidizes into a carboxylic acid. So when we do this on a test, or sorry, on your final exam, wink, 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 but when we do this on paper, we're going to assume we go the complete oxidation. So like, again, if I give you this question on a final exam, we assume that it's completely reacted. So these are in the middle, these are called intermediates. And there are ways to isolate these products, but we will go straight to the end for the test or final exam. I keep saying test, there is no more tests, but there is a final. Okay, here's my deal with you guys, because it's getting late. I know it's like 4:07, 4:06. What I'm going to do is I'm going to show you these examples, and then we'll practice more of these tomorrow. So if these two examples are confusing with, and someone in the chat there, you're actually lost. Well, I haven't done any yet, but even after today, if these two examples are confusing, I'm going to write some out with you guys tomorrow. I think I'd rather do it in tomorrow's class to kind of give me some more time. And maybe we'll look at some questions like on your worksheet tomorrow, because this is too hard. Okay, so I have an alkene. Let's look at it. Let's look at example number 1. I have an alkene here. What you do, and again, we will look at this a little more tomorrow, is you split this double bond. Okay, now when you split the double bond, you add an oxygen to the end of the double bonds. Okay, maybe let's do this on a piece of paper, on a white piece of paper. So hold on now, 1, 2, 3, 4. Let's open this up on the white screen here. Oops, sorry. Okay, I just wanted to make sure I'm drawing it correctly. So here we go. We have 1, 2, 3, I think 4 like this. Oops, and no methyl group. Okay, so we're adding KMNO4. All right, we will end up getting from this 2 products. Now, here's what you do. Watch my red pen and watch what I'm going to do. I'm going to literally cut this chemical in half. Cleavage, I'm cutting it in half. And what I end up getting when I cut it in half is I end up getting this guy. Oh my gosh. I'm going to throw this pen out the window. Okay, so I get this guy, and I get this guy. Sorry. Okay, now notice I kept the double bond there. In the mechanism, like in the step-by-step process, first this would form an alcohol, but we're skipping right to the end here. Okay, so I cut the double bond, I've cut it here, I've cut it here. All you do is, now that I've cut it, I add an oxygen here. Let me pick another color too. I'll use dark blue. I put an oxygen there, and I put an oxygen there. Okay, that's step 2, I guess. So step 1, cut the double bond in half. Step 2, now that you have the molecules split into 2, put an oxygen at the end of the double bonds. Step 3, remember, we're going full oxidation here. Step 3 is, if you have room, add more oxygens. Now, let me explain. Oh no, I hate this. Sorry, guys. Let me just quickly draw that again. When you do this white screen and you go to another slide, it erases it, and I don't know why. Okay, so we're adding KMNO4. So, sorry, just let me draw this again. We're splitting it down the middle. So I get this shape, and I get this shape. You're going to get 2 products. All right, so like I said, stick an oxygen at the end of each. Now, highlighter. Somebody in the chat tell me, that carbon that I circled in orange, how many bonds are on that carbon? Let me know in the chat. Is it 1, 2, 3, or 4? 4. Oh, sorry, Saif mentioned in the chat. When I say tomorrow, I mean Wednesday, obviously. We don't have class tomorrow. Naim, Saif, they all say 4. Exactly. This carbon is completely full. It cannot take any more oxygens. So this carbon here on the top chemical cannot take any more hydrogens. Now, what about the bottom chemical? I'll highlight that. I'll pick a different color here. In the chat, how many bonds are in the bottom carbon? 3, Naim says. And you're correct. There's only 3 here. Trying to be really careful. If I go to the next slide, I'm going to be really mad. So this compound, sorry, I'm going slow because I'm really trying to not skip the slide. This compound only has 3 carbons. That means it has room for 1 more oxygen. And when we write that compound down, it fully oxidizes. We can only add 1 more oxygen, so we add it in the form of an alcohol. So this is done. This is the hardest of the chemical reactions. Okay, so guys, I think I'm going to stop here because I'm really nervous. I'm going to kind of cancel this slide. We will do a little bit more practice on this tomorrow. So if anybody here is really confused right now, we will look at this again tomorrow, and then we'll finish chapter 3.
Yes, sir.
All right. Now, before we go, a couple things. There is no lab. You don't have labs this week. There's only 2 labs left. Your lab 6 and lab 7. So there's only 2 labs left.
So there's no lab tomorrow?
Nope, no lab tomorrow. Your next, and guys, remember, this is posted on your D2L. In your course outline, your course information sheet, I have the lab schedule. The lab schedule has been there since September 1st. Your next lab is November 17th. We're going to do lab 6, and it's on campus. So there is no lab tomorrow, but November 17th that week, we will have lab number 6. Okay, I'm going to hit stop record. If there's any questions, let me know.